G'day viewers. In this segment I'm going to talk about DNS security. And the main protocol we'll look at to secure naming in the internet is this one, DNS Sec, which provides DNS security extensions. Okay, so first we'll begin with a little bit of motivation and get towards a goal and a threat model. The motivation here is that naming is really a critical internet service. We better get this right. This is fairly clear if you think about it, because naming really binds a host name to an IP address. We use it all of the time when we, for instance, surf the web and contact websites. The DNS is used to translate the host name of the website into an IP address. So it can be disastrous if this binding can be compromised and broken so that wrong bindings are returned. Instead of contacting your real bank, you might end up contacting some other site altogether, and this just can't be good. So our real goal here is to secure the DNS, where secure the DNS means ensuring that the returned binding is correct. Now, actually it's quite interesting to observe that this property is all about the integrity and authenticity of answers from the DNS. It's not about confidentiality. Actually, we don't particularly care if the DNS replies are encrypted across the network or not. Since the DNS was a service where anyone could ask for these translations and see it, then it seems fine to return the answers in plain text where everyone can read it. So this is interesting just because it contrasts with the need for confidentiality when we looked at 82.11 and the web. Now our attacker model, the threat here, is that someone in the middle of the network, Trudy here, can intercept and tamper with the messages. And this can cause us to get the binding wrong. It would also be possible to consider some attack models where you compromise some DNS servers, but we're going to ignore all of that for now. And in this quick look, we're just going to look at activity across the network where information is corrupted on the network. Okay, so here's one interesting topic for us to look at with DNS spoofing. Now, you might have wondered this. We're talking about making sure the DNS is secure. But how is it that you can corrupt the DNS in the first place, especially if I'm just talking about an attacker somewhere in the network? I guess if you're an ISP or someone really on the path, you could change messages as they go through. But it turns out that even if you're a remote attacker on the internet, you're not on the path between the DNS server and the other DNS servers it queries, you can still often influence the result. This is called DNS spoofing. And what we do here is the following. Trudy essentially tricks a name server into caching an incorrect binding by using the DNS protocol itself. So we're going to exploit the DNS protocol and misuse it. It's really evil. It's the sort of thing that security is all about. Let's see how it works. So here's DNS spoofing. Don't do this at home. Learn it, but don't do this at home. So this is the setup that we would like to accomplish, and then I'll get to how we're going to accomplish this. We have a local name server. We want to poison the cache here. And by poison the cache, I mean insert bogus information into it that has incorrect bindings. That way, the wrong information will be returned to all of the clients of the name server should they ask for that translation. Now, this name server will be using the DNS protocol to query other DNS servers, like the .com server, and get information. So what we want to do is have Trudy send a fake DNS reply or a false DNS reply, which has a bad binding, back to the name server in such a way that the name server will accept it and put it in its cache. This is great. This is what we want to do. Well, that's all good and well. But to accomplish that, there are just a few questions. You probably start thinking about them immediately as I was sketching that scenario. So here are at least 3 issues that occur to me right away, and they probably occur to you, which we have to deal with. How does Trudy know when that DNS name server is sending a query to other DNS name servers and what it's making the query for? So, because we've got to know that to be able to send the reply. And how can Trudy send a fake reply that looks good enough that it can trick the name server into believing it's the real reply? And then, even if this happens, the real reply from the real DNS system will probably show up sooner or later. If it does, how can we make sure that Trudy's reply is kept in the DNS name server instead of the real answer? Well, it turns out that there are reasonable solutions to all of these issues if you look at the details. And in security, the devil is always in the details. Here's how you could go about solving those issues. So first of all, how does Trudy know what requests the DNS name server is making and to who? Well, for the ones she wants to poison, easy. Trudy can just make the query herself of the local name server, and this will cause it to use the DNS protocol to try and find out. Now, remember that a name server is really some device which works on behalf of a pool of local clients. Trudy can really just act as another of those local clients. You can impersonate a local client and use the services of the name server. Often DNS name servers, local name servers, don't have access restrictions on them because they want to make it easy for many different clients who are part of the local ISP or whatever to use them. Okay, so the second question. How can Trudy supply a fake DNS reply that looks so good that it's taken to be real? Well, this is a bit more difficult. It's more difficult because the local name server, when it gets the reply, is going to do some number of checks. So we really need to understand what they are in detail so we can know how to fool them. I'll tell you some of them. One of them is that we're going to see where the reply comes from. Look at the IP address. It should be from one of the authoritative name servers from whom we were expecting a reply because we sent the request there. That's one issue. The other one is that replies and queries have an ID number that's filled out by the local name server, all of the name servers. So these should match between the query and the reply. This is how a name server pairs them together. And the final issue is that name servers only accept responses when there is a query outstanding. So we need to make sure that we're sending that when there's a query outstanding. But note that there's nothing actually about the content, what this binding is, because the name server doesn't know that. It's just going to accept any reasonable answer. Okay, so here's some techniques we could use to come up with a pretty good fake DNS reply. For the IP address, we'll simply put the IP address of the real name server who should be returning the response as the source address of our packet. Can we do this? Yes. On IP packets, there's a source and a destination address. The destination address is used for forwarding, so it has to be right to take you to the right place. But the source address is often not checked by the network. It's really there for the destination to use and send information back. So if the network doesn't check this, we can spoof the IP source address. What about the ID? Well, the ID is actually only a 16-bit field, so there are only 64,000 possibilities, which is not many for a computer that can send thousands of packets a second. So we could just send a big bag of replies, hoping that one of them has the right ID. And we might only have a small chance of succeeding, but over time, if we try this technique, pretty soon we'll get it right. This actually used to be even easier, and often is, with old implementations. Some implementations used the ID field as a counter. So in that way, if Trudy can just sample about where the counter's at by observing some message, any message that the name server, target name server sends out to another name server, then she'll be able to predict roughly where the counter will be and send only a small number of packets to have the right value. And to make sure that there is a request outstanding, well, we can simply send the reply right away after the query, so it'll get through. When you put these together, all of these techniques have a pretty good chance of succeeding. And finally, there was one remaining issue of what was going to happen when the real DNS reply showed up, the real answer, the one we wanted. Actually, this is likely not a problem, because at this stage, if Trudy has accepted the fake answer, there is no outstanding response as far as Trudy is concerned, so that when the real response arrives, most likely it will be discarded as unwanted or some spurious duplicate. So we're really throwing away the real response and not worrying about it. So you can see when you put all of these techniques together that the DNS can be spoofed. And this is very much a real problem in practice because it can be done, it is done, and the DNS is a critical service, so undermining it causes very bad things to happen. Well, now that we've got our security hats on, let's fix the problem. Actually, rather, let's understand how the problem can be fixed, because people have been working on fixing this problem for a long time in the guise of work on DNS security extensions. And these extensions have very slowly, until recently, been rolled out into the internet, and recently deployment is really beginning to accelerate, so they're being rolled out. Okay, so the DNS security extensions simply extend the DNS with several new types of records. I'll talk about the records in a minute, but there's an RRSig record for digital signatures of records so we can check them, and there are two records which contain public keying information so that we can validate things and delegate from one name server to the other. Now, DNSSEC is something that's been under development for a long time. The first version was standardized in '97. There are actually quite a lot of issues with it, so as people gain experience with it, eventually it was rewritten, totally revised in 2005, and then it's been deployed relatively slowly. Deployment is a little difficult because it requires software upgrades essentially everywhere, like clients as well as all sorts of servers. So it's a fairly big thing to accomplish. But recently, especially with renewed pressure because of the rise of security attacks, there's been a concerted effort. The root servers have all been upgraded to speak DNSSEC and have signed certificates, and this happened in 2010. And now there is a substantial uptick in the deployment of DNSSEC, starting at the highest layers of the DNS on down. So I think now you can attain authenticated information about servers in the .com domain, for instance. So let's learn a little more about DNSSEC. So DNSSEC introduces new records, and these are in addition to the records we've already learned about for the DNS, such as the A records for IP addresses, the NS records for name servers. The new records are the RRSig record. This contains a digital signature of the domain records. So whoever's receiving the information can check the digital signature to make sure that the information in the record was correct. There is also a DNS key record. This contains the public key, which is used by a server to sign records in a zone. So this is the key that we'll use with the RRSig records to check things. And there's also a DS record. This is for delegation server record. This is used by one name server to tell you the public key of another name server which handles a small portion of the space, like uw.edu being inside edu. And finally, there are other records that I'm not really going to get into that provide authenticated denial of existence. So if you look up a name and you find it's not there, you can get an authoritative answer that you can check to learn that it really came from a name server, so that really there is no such address. Now, the interesting question for us really has to do with validating all of the replies. So when a client gets the DNS replies, it would like to validate them to see that it actually has the correct binding. The rest of the DNS just works as usual. So that's what I really want to talk about, how a client, when they get all of the replies, can check that they are the right replies. Well, to do this, we're going to use a method that's similar in some ways to the certificate hierarchy in the PKI used for web security with SSL. We're going to have clients assume a trust anchor to be the root of the DNS tree, the public keys for the root of the DNS tree. This is part of the DNS configuration. In the same way that you had the IP addresses for the root servers, now you have public keying information for all of the root servers. And trust is then going to proceed down the DNS hierarchy. So from one level, we will work out the public keys, and we can check signatures for the next lower level, and so forth until we get down to the level we want. So let's see an example to see how this process works. So just imagine here, our example is that a client queries www.uw.edu just as usual. So it's going to follow the same path as usual and receive all of the binding information. But in addition, it will also receive signatures and keys to validate the answer. So actually the answer is down here, the final answer. You can see that the uw.edu name server returns www.uw.edu saying that it has a certain IP address. And this information is signed. This is the signature, this is the RRSig information. It's signed by the uw.edu server. So now we just want to check all of the signatures, and if they hold, we will then decide that we believe this is a correct binding. So how can we do that? Well, we start at the top. So we're going to validate from the top down. First of all, we have here, we know the key for the root because that's a trust anchor we're configured with. So the root will then tell us information such as edu has been delegated to use a certain key, kedu. Well, we can use the key we have for the root to check that delegation statement. This is signed with the key for the root. If the signature there is okay, then we know the key for the edu level. Now, the edu level then says that uw.edu has been delegated from it with a certain key here, and it's signed with the edu key. So we can check that statement with the right key. And now, if that statement holds, now we know the key for uw.edu. Now, uw.edu has now made a statement about the binding. And, oh sorry, that was this one. We use uw.edu to check uw.edu. And then finally, now that we have the uw.edu key, we can use that key to check the information in the resource record about the IP address to see that the signature for that holds, so that that binding is correct. And if that holds, we've got the right IP address that corresponds to this host name. And we can contact it with a good degree of confidence that it's the right IP address. And there's a lot more in the DNS Sec too. So some other features would just be authoritative answers that a record doesn't exist. These were the other methods I mentioned. There is also some optional anti-spoofing to more tightly bond the query and reply. And there are also flags related to deployment. But in this brief overview, we don't have time to go over them. You can look up that information yourself if you're interested. So some of the takeaways here that I'd like you to remember is just this whole idea of DNS spoofing and that it's possible without added security measures. It gives you a sense of how things can be corrupted in practice, and it's very much a large problem in practice. DNSSEC also as a solution is interesting because it's just adding authentication only to the replies of the DNS, not confidentiality and so forth. And it does this using a hierarchy of public keys. So now you know about DNS security.